Are you trying to develop a new electronic product? Well, you're in luck because in this single workshop, you're going to learn all the steps to develop and prototype a new electronic product. Hi, I'm John Teal. I'm an electronics engineer and the founder of Predictable Designs, where we help entrepreneurs, startups, inventors, and small businesses develop and sell new electronic products. Okay, let's get started.
The first step of designing custom electronics is to create a schematic circuit diagram. So first of all, let me explain what a schematic diagram is. For most of you will know what it is, but I just want to make sure that those that don't have any electronics design experience understand a schematic circuit diagram. The best way to explain a circuit diagram is it's a conceptual drawing that's very much like a blueprint for a house. It's conceptual because nothing that you see here is what you will see on your board. Obviously, you don't see anything that looks like this. It's purely conceptual. The printed circuit board layout, that's the real world part of electronics design, but the schematic circuit diagram is the first step, and that's just a more higher level conceptual diagram. And the key thing that it shows is it shows you how all of the components are connected. This is a very simple schematic that we're looking at here. In fact, I'm going to go ahead and pull this up in my schematic software instead of looking at it here. This is a very simple schematic, like I'd said. This is an STM32 microcontroller. This is a power regulator. This is a USB input. You could supply through a USB wall adapter. This would output a 5-volt DC voltage, which then goes to the TOV70233, which is a low dropout linear regulator. That just takes the 5 volts, sub-regulates it down to 3.3 volts, and then that's what is used to power the microcontroller, because the microcontroller can't be powered from 5 volts. There are microcontrollers that can be, but the STM32, I believe, has a maximum of 3.6 volts for the input supply. We have to sub-regulate the 5 volts down to 3.3. And then this device here is just a programming connector. This is an exceptionally simple design. In fact, it's so simple it doesn't really have a real world application because there's nothing connected to the microcontroller. It's just a microcontroller that's running a program, but there's no LEDs, there's no sensors, there's no communication ports. This is just for an example, but it kind of shows you generally what the types of things that are included in a schematic. You have to place each of the components down, each of the main components. I'm not talking the passive components like the capacitors. You have to place these down, and most of these will have been selected as part of your block diagram that you should have done it in the research planning stage. And then you have to connect everything together. So you can see, and a lot of times you'll see in a schematic where you won't visually see that they're connected, but the trace has the same name, and then that connects it in the software. For instance, this line here coming out of the linear regulator, I've labeled VDD. And you can see that only connects to these capacitors, but you don't see it physically connected to anything else. But what you do see is when I highlight this line, you can see that these also all turn this blue color. This is basically showing that all of these lines are connected to VDD, even though you don't visually see that. And you could draw it manually. You could just draw a line from here and tie it up into this line here. But a lot of times that can make a schematic get really messy. It wouldn't be that big of a deal for this simple schematic, but a much more complex schematic, if you physically draw every line connecting, then it can make for a really complex schematic that it can be kind of confusing to look at. It's really common to name traces, and then they'll be connected in the software. But when doing that, you want to make sure that they are connected. It's quite easy to perhaps have this as a different name than this accidentally. So you want to make sure that they are connected. And one easy way you can see here is when I highlight one of them, all of the nodes connected should also highlight. The other components that are on here are the capacitors. The passives are going to be capacitors, resistors, and inductors. Inductors tend to be more rare. That's probably the least used of the passive components. They're typically going to be used in like switching regulators and for filtering. But what you will see is lots of capacitors and also typically quite a few resistors. This design doesn't have any resistors in it, but it does have a lot of capacitors. And these capacitors are all for basically filtering, decoupling the supply as it goes to the microcontroller. And that's just so that any disturbances on the supply line don't necessarily impact the microcontroller. And then also these supply a local temporary storage of energy. All these capacitors will be placed near the pins, the supply pins of the microcontroller, that if the microcontroller needs a sudden burst of current and the linear regulator, which may be far away, doesn't have quite time to respond yet, then that current will be temporarily supplied by these capacitors that will be placed close to the pin. The other key thing to keep in mind with the schematic is or any electronics design is the fact that there are dozens of different PCB or schematic design software. I'm using one called DipTrace, but that's kind of not a real well-known package. The more common ones would be Altium or Eagle. And the thing to keep in mind is a lot of these packages are not compatible with each other. It becomes very problematic if you want to switch design software in the middle of a design. Just keep that in mind, and this is something to keep in mind, especially if you're outsourcing the electronics design. If you're outsourcing it, then it would be very beneficial to outsource to a designer using a more commonly used design package like Altium or Eagle. And the reason being is it's very common that you'll need to switch engineers in the middle of a project. And if you switch engineers, then it's almost, in most cases, it's going to be best if they can use the same software package as the original designer. If you start by hiring a designer using a more obscure software package, then that's going to complicate things if you have to transition to a new designer. Just keep that in mind. Using less common design software like I'm using, DipTrace is a really good option if you're designing your own board. But if you're going to be outsourcing it and you expect to maybe cycle through different engineers, then I would recommend going with a more commonly used software package like Altium or Eagle. Once you finish the schematic design step, then the next step is to create the bill of materials. And fortunately, this is an easy step because it's auto-generated by your schematic software. Although typically you'll have to, once it's generated, it will output like an Excel file, and then you may need to go in and clean it up a bit, but it will output all of the key data that you need for the bill of materials, assuming you've entered all of that data into the schematic. For instance, you have to have the part number entered for each of the components, and that's not required when you're creating the schematic, but it is something that you'll want to do before generating the bill of materials, so that the schematic, you can just regenerate the bill of materials as needed. You want to just make sure you include all the part numbers and component values and such in your schematic. Then once you have this bill of materials, this will be a document that you'll live with throughout the manufacturing process. It will be one of the key documents that you'll send to the manufacturer, to the prototype shop, but it's also really useful for you estimating or calculating. At this point, it should be more of a calculation and not necessarily an estimation, but calculating your manufacturing cost. We did some estimating of the manufacturing cost in the early research planning stages, but now you've got all the components picked out. You have all the smaller components, the passives, picked out. Now you can more accurately estimate the exact cost of the board. You also know probably estimate the size of the board a little better, the number of pins, so some of the characteristics that drive the cost of the PCB. Obviously, we still haven't gotten all the costs for other parts of the manufacturing cost, whether that be the enclosure cost or product assembly or testing, logistics. All of that is also, it needs to be factored into your manufacturing cost. And there are kind of two ways to do bill of materials. The cheapest, most straightforward way is to just use an Excel spreadsheet. And that's what I'm going to show you one now. Okay, what we have here is the bill of materials. You can see it's listing every component that the design is using. At the top, I'm starting with the more critical components, the microchips, which are typically have a reference designator starting with a U's, like U1, U3, U4. And the reference designator, or RefDes, as you'll see it abbreviated, is just the designator given to that component in the schematic. Let's go back to the schematic. And you can see this device here, this is U1, this is U2, this is J1, this capacitor is C1, C2. Those are the reference designators. For each component, you'll have the quantity of that component, you'll have the reference designator, how to identify it in the schematic, and on the PCB layout, because these reference designators you'll include on the PCB layout as well. Then you'll need the part number, and this can sometimes either be a manufacturer part number or perhaps a supplier part number. Then you'll have the value, which for the microchips, that doesn't really apply. But once you get down into the capacitors and the resistors, then obviously those do have a value. So capacitors in microfarads or nanofarads, and then obviously resistors are in ohms. That's really those 4 columns are the 4 that you really absolutely have to have in the BOM. But there are, other columns or fields that can also be helpful. I also include the package type. This just gives you the package of that particular chip. This is in a 20-pin SSOP package. This is in a 5-pin SOT23 package. A lot of these package designators may not mean anything to you, but they basically are that designate the type of package that the component is in. And then all of the passives they're given a number. These numbers, 0402 is a specific size of a resistor or a capacitor or an inductor. These are common numbers that you'll see. As an 0402 is really quite small. And for most designs, that's probably going to be the smallest physical size component that you'll use. And then 0603s are a little bit bigger. Then 0805 is a little bit bigger from there. But there are lots of different component size numbers. But those are some of the more common ones are the 0805, the 0603, and the 0402. One thing I don't show in here is the price for each of these. So if you're wanting to use your BOM to estimate more accurately or calculate your exact cost for your electronic components, then you could also just include the price of each of these components here, or have that in a separate document, since the pricing isn't really something you necessarily want to or need to send to your manufacturer. You could keep that in a separate BOM that just includes the pricing. This BOM just has the information that you sent to the manufacturer. We've created the schematic circuit diagram. We've generated the bill of materials from that circuit diagram, and now it's time to design the printed circuit board. Whereas the schematic was a conceptual diagram, the printed circuit board is reality, is the real world. It's the physical board that holds all the components and connects everything together. All the components are obviously soldered down onto the board, so it holds them in place. And then all the lines in the schematic that we had looked at, all the connecting lines will be drawn in the real world on the PCB as signal traces. And a PCB is basically, it's stacked of different layers. The minimum is going to be 2 layers. You have top side and bottom side. In that case, for a 2-sided board, you could put all your components on one side, or you could put components on the top side and the bottom side, although that does add a little cost and complexity. If small size isn't super critical, then it would be beneficial typically to keep all the components on one side. But for a 2-sided board, then you could also have the routing on either the top side or the bottom side. Versus a 4-layer board is more common for more complex designs. Once again, you can have the top and the bottom side, which can have components and then also have routing. And then you would also have 2 inner layers that would just be for routing. Typically, one of these inner layers will be just a ground plane, and the other one may be either for routing or maybe just a power plane of some sort. And then you can go up from there. You can do 6, you can do 8, you can do 10, you can do 12 layers. It's always an even number of layers, but you can do as many, 12 I think is about as many layers as I've seen, and that would be an exceptionally complicated board. Most designs are going to be between 4 to 8 layers most likely, with 4 to 6 being really common. And 4 being by far, I think, the most common number of layers. You can do pretty complex design with 4 layers. And keep in mind, there are differences in internal layers versus external layers. For one thing, for doing your power routing, typically that's best if you do that on the outer layers, because the outer layers can carry more current through the signal traces for the same width compared to internal layers. And that's because the external layers, the top side and the bottom side, are exposed to air. They get airflow over them. That helps to keep those traces cool, because that's what will limit how much current you can drive through a PCB trace. It depends on how quickly or how much the trace heats up until it catastrophically is damaged or melts. Internal layers, they don't receive any airflow. The traces have to be, the same size trace can carry less current when on an internal layer versus an external layer. Just keep that in mind. And the PCB is created in the exact same software as the schematic. This is always the case because one of the key features of the software that it's going to do for you is it's going to compare the PCB layout to your schematic to make sure that they electrically are equivalent, that they match each other. And that's very critical. That's not something you want to do manually by hand. You need a computer to do that because otherwise you may have things misconnected in your layout that don't match the schematics. That's really critical. And the software, it performs really two critical checks. First of all, it also does a design rules check. It makes sure that the printed circuit board layout matches all the rules that you've entered. That would be the spacing between traces, the minimum width of a trace, things like that. And those rules vary depending on the manufacturer. So before you start the PCB layout, you want to make sure that you've put in the rules for your manufacturer or the prototype shop that you plan on using. I've found that prototype shops, they can do custom rules, but they also typically will have price discounts if you follow this certain, like maybe an easier to meet standard, like you have really wide traces is the minimum, and then the spacing is larger, so you can get a discount on that. But it's typically, if you go to a manufacturer, they can meet a lot. They can kind of customize the process to match the rules that you've used. But in general, start with where you plan on having these prototype and look up their design rules and be sure that you enter that into the software before you start on the design. You don't want to design your board assuming that you have a 5 mil minimum trace width, and a mil is just a thousandth of an inch. It's a common unit of measure when doing PCB design. You don't want to design your board to use 5 mil wide traces, but then the process you plan on prototyping requires 7 mils as the minimum. You would have to go through and redo your design, or find a different prototype shop, or pay extra and have a custom process done that can meet what you've designed to. Some of the areas with PCB layout that are the most critical, and there's lots of areas that are critical. You can't ever be sloppy in how you do PCB layout, but there are certain types of circuits that are much more complicated and much more stringent on how you design them in the PCB layout. This includes high power, your power regulators, your power management. You need to make sure that this is all laid out correctly with traces wide enough to carry the intended amount of current. It's especially sensitive for switching regulators. If you're using especially high power, high current switching regulators, either boost or buck regulators, then the layout of those circuits are very critical. And in that case, you definitely want to look at the data sheet for that component, and they will usually have a recommended PCB layout. Always follow that for switching regulators. Another complex circuit is wireless. Wireless circuits can be really complicated to design, especially if it's fully custom RF, which is rarely something I recommend. This is one of the reasons it's always usually best to use modules for any wireless functionality. Two reasons: pre-certified modules they simplify the certification process for your product, but they also eliminate all the design complexity and risk associated with wireless circuits. For a fully custom wireless circuit, that's extremely complex, and you want to make sure you bring on an RF engineer to at least review the design. But for most other circuits that will perhaps use a module, the main area that may be complex is wiring up the feed line to an antenna. If you use a module that has a built-in antenna, this isn't an issue. But if you use a module that requires an external antenna or And by external, I don't mean necessarily external to the product. I mean external to the modules. It could be external, an antenna that's visible on the outside of the product, or it could just be an antenna that's mounted on your PCB board, but not on the module itself. That feed line connecting that antenna is very critical and has to be done correctly, as to optimize the power efficiency between the antenna and the transceiver or the radio. So that's very critical. It needs to be, in most cases, laid out to be a 50 ohm complex impedance. And there are specific tools that you can use for making sure that this is done correctly. More complex design packages will include this, but there are other, like AppCAD is one that I use. That's a free tool by Broadcom that you can use to check and feed lines and make sure that they're designed for 50 ohm impedance. Audio is another one that can be complex to lay out, especially when it's in analog format. When you have to be careful about noise pickup with audio. You don't want to route your audio lines, your analog audio lines, right next to a switching regulator, for instance. You have to be very careful with audio, especially when it's in analog format. When it's in digital format, then it's not noise sensitive. That's one of the advantages of digital. This is one of the reasons I prefer digital audio solutions. For instance, use a microphone that already has an analog to digital converter built into it, and it just outputs in an I2S serial communication format. I2S is just a serial communication protocol specifically for digital audio data. If you use a microphone that outputs the audio as digital audio data in I2S format, you can just send that to your microcontroller or whatever, and without any concern for noise pickup. But for any analog audio, you want to definitely be very careful on the PCB layout. And then fast microprocessors that have like external RAM memory, for instance, those can be more complicated to lay out. It's quite a bit different than laying out a microcontroller, because a microcontroller, all the really high speed stuff like the RAM and data bus and address bus are typically internal to the microcontroller. It's something you don't have to deal with as the PCB designer. But for a microprocessor, the RAM is going to be external. It's going to be on a separate chip on the board. You're going to have a data and an address bus. And these, especially if you have a really fast gigahertz microprocessor, these buses, the data and address bus connecting to the RAM, or the layout for these is very, very critical. You have to make sure that all the signals propagate at the same speed. You don't want one data line to be twice as long as all the other data lines. So there's lots of PCB design requirements when you're doing a microprocessor layout. Just keep that in mind. High power, specifically switching regulators, anything wireless, especially custom wireless, but definitely for a lot of designs, the antenna feed line are going to be critical. Analog audio, and then fast microprocessors. Those are some of the more complicated circuits that you're going to have to deal with. And these are, if your design uses any of these, then you definitely want to make sure that you follow the guidelines for these types of designs, or bring in someone to help with these more complex parts of your design. I'm going to look at now the PCB layout in DipTrace, the design software that I'm using. This is the PCB layout that was for the schematic that we had created. That's quite simple, just a microcontroller and a power regulator. If we go back here, I'll just kind of quickly go through this to kind of give you an idea. These blue lines are called rat lines, and they just show a direct, like this pin, you can just follow the line and tell where it connects to. These are just sort of for visual guidelines when you're doing all the connections. You can see how the things are connected before you draw on it, the signal traces. These blue lines are not really there. I'm going to go ahead and turn off rat lines just because they kind of make it a little ugly of a design. This is the USB connector. U2, this is the linear regulator that takes the 5 volts and outputs it to 3.3. Then this is the line, this line here is the VDD line. That was this line here in the schematic that goes to all these capacitors, it goes to the microcontroller, and it goes to the programming connector. That's this trace here, and you can see how it ties into the microcontroller, and it ties in through these decoupling capacitors, which you can see are placed right next to the pin. Here's a C4, C5, and they go right next to this pin. The same with these two capacitors here, and then these two here. Each of the microcontroller power supply pins has two decoupling capacitors. And one is a larger capacitor, like a 4.7 microfarad on each pin, and then there's also 100 nanofarad. And the smaller capacitor is typically used for filtering out any high frequency noise. These are all connected by the signal traces, and this is a very simple 2-layer board. I've got most of the traces are connected on the top layer, and you can see this is the layer I've got all the components on. But if I flip to the bottom side, you can see it's still showing the components and stuff that are on the top side, but they're kind of grayed out. So you can see the only thing I've got on this bottom side are these three signal connections. It's pretty simple, but you could, in theory, have some of these components on the back side of this board. But for something this simple, and obviously I've got tons of empty space, this wasn't a space optimized board. But this gives you kind of a quick, easy to see example of a PCB and how it's connected. You have the signal traces, and then what you have here are these vias. Via is basically just a hole through the PCB that has metal placed inside of it. Now it allows the signal trace to pass through the board from one layer to the next. You can see this signal starts on the top layer, has a trace that goes to this via, but now if I switch to the bottom layer, you can see this via comes to the bottom layer. Now the trace goes on the bottom layer until it hits another via right here. This via is going to take the signal back to the top layer. Let's transition back to the top layer, and you can see on the top layer it connects it right to this pin. That's a via, and these are through vias, which is by far the most common type of via, and most designs will only use through vias. And a through via is a via where it goes through all layers. So even though for this board, it's only 2 layers. There's, you don't have another option. But let's say you have a 4-layer board, and I need a via to connect a signal trace on layer 2 to layer 3. Well, with through vias, I can't do that. I have to draw a via that would go through all 4 layers. Even though that via goes through all 4 layers, it's only connected to layers 2 and 3. It doesn't connect to anything on the layers 1 and 4, but it does exist there. It takes up space. These through vias can when you have more complex designs, they can take up quite a bit of space. In cases where space is extremely critical, and I have to say it needs to be really critical because what I'm going to suggest can drastically increase your cost, especially your prototyping cost. But you can use vias that are called blind vias or buried vias. And these are vias that don't go through all layers. They may only go from layer 2 to layer 3. But maybe 95% of designs shouldn't use blind vias or buried vias because they don't add a whole lot of benefit other than maybe decreasing your board size a small amount. It has to be only used in cases where every fraction of a millimeter in board size is critical, because otherwise it can pretty much double your prototyping cost. Here's a picture of a printed circuit board. This isn't the one that we've been looking at, the schematic or the PCB, and you can tell this is quite a bit more complicated, but you can see the same thing. This would be a microchip here, perhaps a microcontroller. You can see the signal traces, just like what we looked at on the PCB. All of these are capacitors, and then these are the vias that you can see. The signal trace comes down in vias and goes down to a different layer. Then, of course, there are other aspects of the board PCB design I didn't mention, such as mounting holes. So you can see this is where the product mounts into a board. It looks like they're tying this to. This is also ground. You can see this looks like perhaps a ground plane here, and then their mounting bolts connect in with the ground, and then this is what holds it into place. Okay, that wraps up the electronics hardware design, at least the initial design. You have to keep in mind that all of this is going to be an iterative process. You don't just go schematic design, BOM, PCB design, and then you're done and it's ready for market. You're going to have to prototype it and test it and debug it and revise it. And those are things that we'll get into later in the prototyping stage. Next, we're going to look at how to develop the software required for your product. There are different types of software depending on your specific product and application. Most products are going to have what's called firmware, and firmware is the software that's embedded inside your product. It's running on the microcontroller that serves as sort of the brains for your product. And typically embedded software or firmware is going to be, it's low level. By low level, I mean it ties closely to the hardware. Because of this, it tends to require a solid understanding of the hardware. Most firmware programmers that I have worked with tend to be electrical engineers and not computer scientists. They're electrical engineers because they have the fundamental understanding of the basics of the hardware. Most embedded firmware is going to be written in either C or C++. And typically, so for instance, an Arduino, when you connect to program it, you connect through you will use the Arduino IDE or integrated development environment, and then you will connect directly to the Arduino through a USB. So you just have basically a USB cable from your computer going directly to the Arduino. Well, that's not how most products are programmed. The Arduino added the ability to have a USB just to simplify for makers doing the programming, to not require any special equipment. But for most products, when you're designing with a custom product with a microcontroller, you're going to need what's called an in-circuit programmer or in-circuit debugger. And it looks like this. This is one that's common for the STM8 and STM32 series of microcontrollers from ST Microelectronics. It's called the ST-Link, and you can see it's basically just a little, this is once again called an in-circuit debugger or in-circuit programmer. And this connects to your computer through USB, but then it connects to your board through the native programming interface. Either a JTAG is common, or what's called a SWD or single wire debug. Those are two protocols used to connect to microcontrollers. JTAG being the most common and more of the industry standard. You'll need a device like this ST-Link to allow you to connect from your computer's USB port to either a JTAG, most likely, or perhaps an SWD connection on the board itself. That's the embedded firmware. And like I said, this is typically much closer operates to the hardware. Whoever does this needs to have a solid understanding of the hardware. You don't have to wait to get your custom hardware design prototypes back before you can begin programming. You'll need your boards to finalize the program and to test everything out, obviously, but you can begin developing the firmware in advance or in parallel while you're developing your hardware through the use of development kits. For instance, the STM32 microcontroller series from ST Microelectronics, they offer a wide assortment of development boards that are based on the different STM32 microcontrollers that they have. And this allows you to get a head start, and you can begin developing your code using one of these development boards. But like I said, you will still have to, once you get your final hardware back, then you'll have to tweak and modify your program and test it using your final hardware. But at least with the development kits, you can get a head start on that. And it doesn't have to be done sequentially. You don't have to design your schematic, design your PCB, order prototypes, get those prototypes back, and then start doing programming. Instead, you can start that much earlier in the process to allow you to speed up the time to market. In addition to the firmware that is running embedded in your product, and I should specify that I'm assuming that it's a microcontroller based product, that's the brains of your product. You don't have an operating system. If your product is more advanced and requires a microprocessor running an operating system like Linux, for instance, or Android, then that's going to be a bit different. Then it becomes much higher level programming than it would for a microcontroller, because the operating system has taken care of doing a lot of the low level development. If you're using a microprocessor that's running an operating system, then the programming required will not be as low level as it is if you're running a microcontroller product without any type of operating system. If you have an operating system, then most likely you would probably, there are still electrical engineers that can do all types of programming, but since you're moving away from requiring a solid understanding of the hardware, you tend to get more into the realm of computer science and programmers than you do than electrical engineers. Just keep that in mind. If your product is using a microprocessor with an operating system, then the requirements for the firmware are going to be quite a bit different than if you're running a microcontroller without an operating system. In addition to this, the embedded software that runs inside of your product, and for a lot of products, this will be the only software that you require. But if your product is going to interface or communicate with a mobile app, then you also have to take into account the mobile app software development. And this is a totally different world to developing firmware. So first of all, it's much higher level. It doesn't require any understanding of the hardware really. And it tends to be more the realm of computer science and programmers. There are lots of companies out there that can develop mobile apps that have no understanding of how to do firmware. If you're lucky, you can have the same. It would be ideal if you find a place that does both. If it's a design firm that you're working with, then they're gonna have people that can do both firmware and mobile apps. If you're dealing with a freelancer, then the odds are that you're going to have to hire someone separately to do the mobile application. Since there are exceptions, you'll find some engineers that can do both firmware and mobile apps, but they tend to each be very specialized. So you're most likely going to be best finding someone for each of those steps. And then not as common, but you will also for some applications have computer software. If your device interfaces or communicates with complex PC software, then obviously that's going to be software that you're going to have to develop as well. And then finally, there can be also like cloud service level programming. If your product has internet access and connects with the cloud, then there'll be programming required for that as well. And that, like computer software, tends to be very high level, more computer science majors than electrical engineers, and it doesn't require an understanding of the hardware. But for most projects, the firmware is going to be the main software that you have to develop, and that's where the emphasis is going to be. That will be the software you develop first. You can develop a mobile app early on as well, but typically it's best to get the firmware going, and then you can start on the mobile app once you've got the hardware and the firmware running for the most part, and you've confirmed and tested everything is operating close to how it's supposed to. Then at that point, then you can begin programming the mobile app and having that interface with the firmware. Now that we have finished the initial electronics design, we're going to move on to the design of the enclosure or the case or any custom plastic parts that your product requires. First of all, you need to understand that the technology used for prototyping custom plastic parts is totally different than the technology used for production or high volume production. For prototypes, you're going to be using either 3D printing most likely or CNC machining. And 3D printing, as you may or most likely know, is a layering process. This 3D printer uses a molten resin, and it basically builds your product or the part up layer by layer. CNC machining is the opposite. 3D printing is considered an additive process. The part is built by adding layer upon layer. CNC machining is a subtractive process. What it does is it starts with a solid block of plastic, and then they basically carve out your part from that block. It's similar to like a sculpture. 3D printing is the most common of those two methods used for prototyping, but CNC machining has some advantages in regards to it allows you to use a production plastic. You could basically buy a block of plastic that would be identical to the plastic that you use in production, versus 3D printing uses prototyping resins in the 3D printer that are designed to emulate production plastic, but they are quite a bit different. So That's something you need to keep in mind, is if things like the plastic, the look and feel, the way things snap together, those are all impacted by the type of plastic being used. So if the type of plastic being used is really critical for your product, then you may want to perhaps start off with 3D printing, but then eventually transition over to CNC machining. You can get prototypes built that are made using the same plastic that will be used for production. Now, for production, it's a totally different story. For production of custom plastic parts, you're going to use high pressure injection molding. And this is a really old technology that's basically a mold that's made out of metal, typically steel, but lower cost ones can be made out of aluminum, that has a cavity inside of this mold, and the cavity is the shape of your part. They inject molten plastic at high pressure into this cavity inside your mold, and the high pressure is used so that the molten plastic goes into every little nook and cranny of your cavity that forms your part. That molten plastic is injected at high pressure, it's allowed to cool, and then the mold is opened up and the part is removed. It sounds really simple, but there's a lot of complex restrictions on injection molding, and I'll be getting into that in more detail here shortly. But the thing to keep in mind is you cannot design your product solely looking at 3D printing or CNC machining, because what you can 3D print is totally different than what you can injection mold. First of all, 3D printing is not very restrictive at all. You can design a 3D model and have 3D printed very elaborate parts but you can never actually manufacture those parts using high pressure injection molding. Or perhaps you may be able to, but now you've required a much more complicated mold than if you would have taken injection molding into account from the very beginning. Then you could design your products as to simplify and lower the cost of the injection molds that you'll need. And I'll like I mentioned, I'll go into that in more detail as well. You don't necessarily, your first prototype doesn't need to be ready for injection molding, but because there's a lot of fine details that you'll do to the part at the very end once you've perfected it to make it ready for injection molding. But you need to have a fundamental understanding of injection molding from the very beginning, because what commonly happens is people will either do it themselves or hire a 3D modeling expert who knows nothing about injection molding, and they'll design this great enclosure or part for your product, but then when you go to actually have it injection molded or manufactured, you realize it's nowhere near being ready for manufacturing or injection molding, and the design has to be redone from the very beginning. And that's obviously not something you want to have happen. That's why you need to design for injection molding from the very beginning of the design process for the enclosure. Some of the restrictions in regards to the enclosure or enclosure design or any part design when it comes to injection molding. Some of the things we'll be looking at are called undercuts, draft, injector pin marks. You have to have uniform wall thickness, radius or chamfer the corners, and there's a parting line. I'll go through each of these in detail. But let's first start by, let's take a look at a 3D model, because this is where it all starts, is with the 3D model. I'm using Autodesk Fusion 360, but SolidWorks is another one. And in fact, SolidWorks is the one that I have the most experience with in the past for my own product, but I don't really do 3D modeling anymore. I don't have SolidWorks anymore. I'm using Fusion 360 from Autodesk. This part is just a sample part. It's obviously not an enclosure, but it allows you to see what a 3D modeled part looks like, and so you can rotate it around in any direction. It's obviously a 3D model, so you can rotate it in 3 dimensions. But this part easily demonstrates one of the complexities, or one of the key complexities with injection molding. And although injection molding sounds really simple, one of the aspects of it that require a lot of limitations on what can be designed is the fact that the part has to be able to be removed from the mold easily. Let's say you were molding this part here. You have 2 halves of the mold, and let's assume that the mold is going to pull apart in a vertical direction. The top half of the mold will go this direction. The bottom half of the mold will pull this direction. Let's look at these slots here. The slots would be no problem because you could have a piece of the mold that fills in this slot. The plastic doesn't go in here, and that part of the mold can be easily pulled up or pulled down. This type of mold to make this part is just called a simple pull mold. It's a mold that can just be simply pulled apart and then the parts can be ejected. However, this through hole here and then this through hole here that you see right here in the back, right here, those are cause complications because they create undercuts. When the two halves of the mold come together, wherever you don't want plastic, there has to be metal. That means inside of this hole here and inside of this hole here has to be a piece of the mold has to fill that in. However, if the mold is pulling apart this way and this way, you would never be able to remove the piece of the part from the mold because part of the mold is actually inside of this hole and inside of this hole. You can never actually remove it. This type of part would require what's called side actions. Instead of a simple pull mold, what you have is now you have these side actions that come in and help basically fill in these parts here. Let's say you wanted to make this part. What you would have is the mold would also, in addition to the top and the bottom that pull out, there would be these side actions. A piece of the mold would come in and that would fill in this hole here, so plastic doesn't enter there. And then you would have another side action that would basically slide in to this hole to keep this hole from filling with plastic and therefore forming the hole. Well, these side actions are mechanical pieces so when the mold is closed, then these side actions are pushed in so that this hole doesn't fill with plastic and this hole doesn't fill with plastic. But then when it's time to remove the part, instead of just opening the mold and pulling it out, you now have to remove these side actions. The side action would be pulled out, and then this side action would be pulled out, and then the mold would be pulled apart and the plastic piece would be removed. Well, this adds a lot of complexity because now instead of just a simple mold with just two halves and no moving parts, you've added moving parts to the mold. These side actions have to be taken in or pushed in and then pulled out, and this adds a lot of complexity to the mold, and molds are very expensive. So complexity equals more expense. This can be a really expensive thing to do is to design your product to require side actions. In almost all cases, it's much better if you can design the product to not require side actions. And there are different tricks that you can do to make this possible. I'll be covering each of these different things that we're going to look at. Undercuts it will be first, though. As I described, an undercut is an area where you basically can't pull the part out because the mold is blocking it from being pulled out. Let's take a look at a snap. So this type of snap is very common. And what you'll see is underneath the snap part that overhangs, this part here is an undercut area. You would have to have the plastic of the mold fill this in to keep this from filling with plastic. But then if you pull the mold apart in the vertical direction, well, you can't pull the mold out because it's going to get stuck on this part that's overhanging, and you can't pull it out the other direction because there's a floor here. Well, one easy way around that is to just put a hole here underneath of the snap. Now the part of the mold that goes in here to keep the plastic from filling in this section, that part of the mold can just be pulled out through this hole. You've essentially eliminated the undercut by adding this slot underneath the undercut region. That's one trick that you can do to remove undercuts. Another thing that's required for an injection molded part, in order to be removed from the mold, let's assume that whether it's a simple pull mold or a mold with side actions, to be able to remove the part easily, you have to add what's called draft. And draft is just a very slight 2 to 3 degree angle that you put on the walls that are vertical and parallel to the direction of the pull of the mold. Let's say, for instance, this part up here at the top. So you're going to have a top piece of the mold and a bottom piece of the mold. Well, to make the part slide out more easily, you can see they've added this angle here. Now this bottom half of the mold can pull out more easily than it could if there were no angle here. The draft is just a small angle. Every product that you have that you've purchased that has custom plastic has this draft on it. You just don't see it or notice it because it's such a fine angle, but it's something to keep in mind. Same is true with this part here. The mold fits around here to form this piece here, but then it can be a little bit complicated, a little difficult to remove the part from the mold. So if you add the angles to this wall, then this will allow the mold to be, the part to be more easily pulled out of the mold. The same is true here with this hole, through hole, where the mold is going into this through hole to block plastic from going in there. Once again, if it's a straight edge, it will make removing the part more challenging. You just add a very small draft angle. They're saying a 1/2 degree minimum. That's pretty small. Typically, I see more like 2 to 3 degrees. So draft is something that you have to take into mind. This is normally not something I recommend doing on your initial design when you're prototyping, because adding draft just complicates the model. It makes making any changes to it more complicated. And fortunately, draft is something that you can easily add to the design after you've finished prototyping. It's just, draft isn't something you typically have to think about too much up front, versus undercuts and uniform wall thickness and all the other issues that we'll get into are things you need to design for from the very beginning. Another important requirement for injection molding is uniform wall thickness. And the reason for this being is you want the plastic to cool off uniformly. In this first part, if you have this huge block of plastic and then you have these thin walls, well, what happens is these thin walls will cool off quicker than once the plastic's injected and it's molten, it's hot, then you have to allow the part to cool. During this cooling process, these thin walls will cool quicker than this huge thick block. And what that does is that creates a temperature differential between the thick parts and the thin parts. And that temperature differential causes the part to warp as it cools. That's the main reason you don't want to have thick areas and thin areas. Also, having uniform wall thickness allows the plastic to flow uniformly into the mold. So you would just have the plastic fill in uniformly if it has uniform walls, versus this section here will take longer to fill in, obviously, than these thinner sections. What you do, and you'll notice this once again on any product, if you take apart a product, you'll see little things like this done, and it's all to keep the uniform wall thickness. Instead of having this as being a big solid block, see, they've carved it out. They've made a wall here that's uniform, and then they have this circular wall that's also supposed to be of uniform wall thickness. And that basically most importantly allows the product to cool uniformly. It doesn't warp. Here's another example. You can see this is like a side shot, that you have these thick sections here. Well, instead of doing that, it's much better to split them into multiple uniform thickness walls. Same here. You can see this part here. It's a decent amount of redesign, but the point is they were redesigning the part to get rid of these thick sections. This once again has a uniform wall thickness. In addition to maintaining uniform wall thickness, the other thing you want is you don't want straight edges. You don't want 90-degree turns, because the plastic has a difficult time filling in that corner and making a really sharp corner. Instead, what you want to do is you want to add a chamfer or just round the corners, but you need to round it where the wall thickness remains uniform. You can see in this case here, if you round the outside corner but not the inside, then now you have a thin section here that doesn't match the thickness over here. In this other case, you can see they've rounded both, but now this section here is thicker than this section. That's going to cause some warping. Whereas this final design, they kept it so that it's an entire uniform wall thickness through the chamfered corner. And this is the correct way to do it. So that is an overview injection molding design, or creating your 3D models. It all starts with a 3D model. You'll most likely start with 3D printing for prototyping that model, but you may eventually want to migrate to CNC machining for those prototypes, so you can use the final production plastic. And then finally, for production, you're going to do high pressure injection molding. As I said, you don't have to have the early prototypes completely ready for injection molding. They don't need things like draft angle, for instance, and perhaps some of if you did this case here for 3D printing instead of this, that would probably be okay because that's a fairly easy change. But you don't want to do anything that requires like really drastic changes to the design to get it ready for injection molding. You just need to keep the fundamental things in mind when designing the product. And the most important and the most critical and the complex is the undercuts. You have to eliminate undercuts, which isn't always possible. There are molds that will require side actions, but in general, it's definitely worth the effort and the time to design your product or your 3D model so that side actions aren't required. In most cases, you can, if you're someone that really understands 3D or injection molding, can design a part so that no side actions are required. Just because keep in mind, side actions are going to drastically increase the cost. It's going to lower the reliability of the mold because now you've added moving parts, and that just adds a lot of extra complications. Just be sure when you're designing your 3D model that you or the 3D modeling designer has a solid understanding of injection molding. Getting an independent design review is one of the best things that you can do to eliminate or at least reduce any design errors. Every established tech company has a procedure for formalized design review. I know when I was a design engineer for Texas Instruments, all designers, we had to present our design to the rest of the engineering group or design group to get their feedback on the design. So this is something that I find that most smaller companies don't do, or people that are hiring freelance engineers definitely don't do this. And I have never met any freelance engineers who have this built in where they already have another engineer review their work. This is something, regardless if they do, just to protect yourself, you should always get an independent review of the design, because this can not only save lots of time and money because it will eliminate the number of prototype iterations that you have to do. It's much better to find any design issues in the design before you prototype than after you prototype it, because then it becomes more costly because now you have to fix it and then prototype again, and prototypes, the cost add up. The other big advantage of getting an independent design review, especially if you're outsourcing the design to freelancers, is it protects you, and it keeps you from being ripped off or scammed or paying someone that's producing garbage design work for you. Unless you have the technical skills to be able to judge the quality of the design work that you're outsourcing, then you definitely want to get independent design reviews, and that can go a long ways in saving you money and preventing you from paying for something that isn't worth the money that you're paying for it. It has all these advantages. It also speeds up your time to market, because the fewer prototype iterations that you require, the faster you're going to be able to get your product to market. And these independent design reviews should be done definitely for the electronics, but also for the enclosure. The enclosure would be mostly a review from a design for manufacturing standpoint, looking at the things that we discussed. Can it be as a simple pull mold? Does it have uniform wall thickness? Does it have draft? Does it have any side actions? Those are all things that an independent design review can help you to identify and eliminate those if those haven't been taken care of in the enclosure design. Always get an independent design review, regardless of whether you're doing the design, you're outsourcing the design, or you're hiring a firm. In most cases, you're only talking a few $100s to have someone review the design, yet it has the potential to save you thousands of dollars. Prototyping a printed circuit board consists of two separate steps. The first step is to fabricate the board itself. So without any of the components, this would just be the stacked up layers that make up the PCB board, whether that be 2, 4, 6, 8, 10, 12 layers. Then obviously all the signal traces connecting everything. And then is the landing pads for each of the components that will be soldered onto the board. That's the first step, is to produce the empty PCB. The second step is the actual assembly of the board. And this shouldn't be confused with assembly of the overall product. This is just assembly of the PCB board itself, basically soldering all the components onto the board. There are different ways you can go about this. First, one option that isn't really feasible for most projects is to do this yourself. You could potentially purchase the empty boards and then solder on all the components yourself. And this can be one, if you're good at soldering and your design is quite simple and it doesn't include any leadless components, then this may be a viable option for you to do the soldering yourself, because the board assembly is going to be the most expensive part of the process of having a board prototyped. You could do that as a possibility to do it yourself, but that's very rare and not something I recommend, because then if there's a problem with the design, you're going to be questioning whether it's a bad solder joint, was something done incorrectly in the assembly process, and so you're going to be second guessing yourself. It's much better, I feel, to outsource the PCB production, both the board itself and the assembly process. And then that just eliminates any complications in debugging as far as being concerned about the quality of the board assembly itself. And secondly, eventually you're going to have the boards mass produced. The method that's used for producing prototypes when you purchase them from a prototype company is the same procedure that's used for production. It's a good, you're going to have to go this route eventually. The earlier you transition to the production process, I feel like the better off you are. So if you're going to outsource your PCB production, then you have two options. You could either do it domestically or you could do it offshore, likely in Asia. And previously, I almost always recommended that you do a PCB prototyping domestically, but because of the limited budgets that so many entrepreneurs are dealing with, and because of the availability of more reputable, well-known Chinese or Asian-based prototyping companies, I now feel for most people, I think that outsourcing it to an Asian production or Asian prototype company is going to be your best option. The main reason being that the cost. Prototypes of PCB, especially the PCB, the board assembly, can be quite expensive. And if you order prototypes from, say, a U.S. company, you can easily be into the $1,000 to $2,000 range. So, and you have to keep in mind that you're going to require multiple iterations of the prototype. This cost of $1,000 to $2,000 is going to be multiplied probably by 3 times, 2 to 3 times at least. It can be very cost beneficial to have the PCB board production done in Asia. The one downside is the shipping time. It's a little more, there's going to be a little more logistics to get the boards to you, but I feel like that's very minor. I don't think for most projects a day or two here and there is going to really make any significant impact. I would advise that most likely go use an Asian prototype company. Some of them that I have experience with are Seed Studio. They do both production, they do prototyping, they do PCB prototyping and 3D printing. They offer a wide suite of services, prototype and production. PCB Way is another Asian PCB manufacturer that I have experience with that I can recommend. And then Bitly is another one. They are actually headquartered in Canada, but they have their manufacturing facility in China. That's another good option. And then Sunstone is a U.S. company that I've used quite a bit in the past. They're going to be a lot more expensive than Seed, PCBWay, or Bitly, but if you're looking for really high quality boards done domestically in the U.S., then definitely check out Sunstone Circuit. When prototyping your PCB, you need to start with very small numbers your first revision, 3 to 5 units. You don't want to go any higher than that, because most likely there's going to be some issues with your first revision. You don't want to produce 10 boards. You don't typically need that. Start with 3 to 5, evaluate those, fix any problems, then iterate your prototype again. And each time you iterate your prototype, you can ramp up the volume. The first time may be 3 to 5 units. The second time you may do 5 to 7 units, and then the third time you maybe do 10 units. Just start small and ramp your way up each time you iterate, and your confidence level that the boards will be usable increases, then you can increase the number of prototypes that you order each time. Now we're going to be looking at prototyping the enclosure or the case for your product or any other custom plastic parts required for your product. There are different technologies used for prototyping the enclosure or any custom shaped plastic parts. The most common is going to be 3D printing. And you're probably familiar with 3D printing. It's an additive process. That means that the part is built by adding layer upon layer of molten resin until it forms the final product. That's the most common prototyping method. It tends to be the simplest, the most widespread, the cheapest to do. It has quite a few ifs with it. The first being that it's built layer by layer. It's a different process entirely than your production units will be, which is injection molding. Therefore, the units are going to look different. They're not going to have the same finish as in a high quality appearance as the final product, the final production part will have. So 3D printing, it also, the resins that it uses aren't the same plastic that will be used in the production part. A lot of things will feel different, how pieces snap together or how strong things are, the flexibility. Those will all be different in your 3D printed prototype versus production. But it's usually it's the best place to start for your first prototypes because it's the kind of the simplest and the most common. So start with 3D printing, iterate with that until you've gotten all the information that you can out of 3D printing, and then you'll want to transition up to the next level of prototyping technology. That next level may be CNC machining. And you may want to start with this instead of 3D printing, but I think most products are best started with 3D printing. And then if the plastic material itself is really critical, let's say you have snap fits and you need to get them just right so they snap together. They don't come apart real easily, but when it so snaps together that it makes it so difficult that you can't snap it. If you need to test things like that, then look at CNC machining. And CNC machining is a subtractive process. That means it starts with a solid block of production plastic. So this would be the same plastic you would use when you're mass producing your part. It starts with a block of that, and then you remove away the plastic or sculpt it basically to form the shape of your part. It's a subtractive. You start with more material than what you'll end up with, and then you're just like carving away or sculpting away. This can be a good transition. It's not going to be for high volume. It's not going to look like, production products as much as some of the other methods that we'll look at, but it's definitely a good step to take after 3D printing if the plastic itself is important for your product. The next option we're going to look at is urethane casting. The first two tend to be for low volume, 3D printing, CNC machining. You may do 3, 5, 6, 7 units, typically less than 10 units that you'll use for those. But like I said, they don't produce parts that are going to look as nice as the production part. So the challenge is getting production parts. You don't want to have to do injection molding because that's going to have a really expensive upfront cost, injection molding, for the cost of the molds. Urethane casting is a nice intermediate way of getting parts that are molded parts that will look closer to your production parts and have the same finish as the production parts, but yet they don't have the complicated or expensive mold requirements. Urethane casting, it starts off by, first of all, you take a 3D print version of your part or a CNC machine version of it. That's how it starts. Then they take that and they basically, using that, they build a mold out of silicone. Silicone is soft, rubbery. They build a mold that's out of silicone using your 3D printed part. You will end up with a mold that has a cavity in it. First of all, the mold's made out of silicone and it will have a cavity that's the shape of your part. Then they can put urethane in that mold and form molded parts of your product that are made out of urethane. You'll see this called urethane casting, silicone casting, vacuum casting, because they use a vacuum instead of high pressure like an injection mold. They use a vacuum to pull the material into the mold and make sure that it fills in all the nooks and crannies. It accurately reproduces the part. That can be a really good option to transition from prototype, but you need some samples, high quality samples to show customers, but you don't yet want to spend thousands on injection molding. Then urethane casting is a good intermediate step. Once again, as with the PCB prototypes, you do have the option of should you use professional prototype shop or should you try to do this at home? Well, First of all, CNC machining isn't going to be feasible. I don't know of any at-home CNC milling machines, and I don't believe urethane casting is going to be practical to do at home. The one that is practical is 3D printing, because you can buy at-home 3D printers now relatively low cost. And that can be really beneficial, especially in the early stages of your prototyping, because it allows you to iterate really quickly. You can produce a prototype, test it out, hold it in your hand, get a feel for it, make the changes to your 3D model, then within minutes or hours you can have an updated model. And that allows you to iterate really quickly, and you can make a lot of progress. That's one of the fastest ways to get through development, is to iterate a lot. Iterate your prototype a lot, and that can be a way to speed it up. That tends to also add a lot of cost to the development process also, but if you have your own printer at home, then that becomes much more economical. If you do decide to have a professional prototype shop do it, then you could either go Asia or domestic, and each has its advantages, just like with the PCB prototypes. If you do it domestic, you'll have it shipped to you much quicker, and that allows you to iterate much quicker. I find with the Enclosure, it becomes a little more beneficial to be able to iterate really quickly compared to the PCB, because the PCB iteration tends to take a lot of time to figure out the fixes and the problems for the next iteration. You don't benefit quite as much with PCB prototyping if you do that at home yourself as you will with prototyping your Enclosure. If you do decide to use a prototype shop, either from the very beginning or after you've gotten as much information as you can from 3D printing your prototype using your at-home 3D printer, perhaps you need to upgrade to either a better 3D printer or a CNC machine or urethane casting. Then at that point you may want to upgrade and switch over to a professional prototype shop. And some that I've used are Seed Studio. Again, I mentioned them before. They do PCB prototypes, PCB production, 3D printing. They have a wide variety of prototype and production services. Proto Labs is a company here in the U.S. that I've used quite a bit in the past that can produce both prototype parts, and then they also do low volume injection molding. That can be a good option for you after you've done the urethane casting, and now you need maybe hundreds or thousands of parts, because urethane casting is only good for about 20 to 25 parts because the silicone molds are so soft and not very durable. They don't last but more than 20 shots or so. And then Ico mold is another one that I've used successfully. Now it's time to finally begin evaluating your prototypes. In the previous steps, we looked at ordering or prototyping both your PCB and your Enclosure. And now we're going to be looking at evaluating the PCB prototypes once you get those back. The first thing to keep in mind is no design is perfect the first time. I've never seen a product go to full production or make it to market on the very first version. That's just not feasible or practical. Don't count on that, or don't anticipate that happening. There's always going to be some type of small issue that's going to pop up in your evaluation. It doesn't matter how careful you are, how many design reviews you have up front, how good the designer is. The odds are very high that there's going to be at least some minor issues with the first version, and likely the second and perhaps the third. It depends on the complexity of the product itself. These revisions and tweaks are always necessary. You just have to plan for it. It's going to require multiple iterations. What will happen is you order the prototype, the PCB prototypes, you get them back, you evaluate them, you identify any problems that you found. Then you have to come up and figure out solutions, design changes you want to make to fix those problems that were discovered. You'll go back, update the schematic or revise the schematic design, perhaps revise your BOM, revise your PCB layout with these changes, order new prototypes, and then begin the evaluation process again. And that will repeat over and over until you finally get prototypes that are completely bug-free. One thing that can be really helpful is don't wait until you get your PCB prototypes, you have them on your desk, and then you begin thinking about, okay, what do I want to test other than the most basic function? beforehand, before you even get your prototypes back, it's really wise if you could take the time to come up with a test and evaluation plan. Just list out all the different characteristics of the part that you want to test, and have that written out ahead of time, so that when you get the parts, then you'll be much more efficient with your evaluation, because you've already thought about all the things that you want to verify. That's a much better procedure, or much better strategy to follow than just winging it and just testing things as you think of them once you get the product. So definitely always try to plan up front for a lot of steps, and that's always going to make your time more efficiently used. I find that this step, the evaluation, debug, and then iterating the prototype, that is the most difficult part of this entire process to forecast. And that's because you're dealing with unknowns. If you knew the problems that were going to exist in your prototypes, then you would never design them to be in there in the first place. You would have solved these problems. By its very nature, when you're prototyping and evaluating and finding any problems, those problems were unknown to you. Because you're dealing with unknowns, it becomes really difficult to forecast that. Not only do you not know the problems that you're going to find yet, but you also don't know the solutions. So you'll likely find some simple problems that have simple solutions, but you may run into a problem that has a complex solution that's going to take you considerable time to figure out a workaround for. That's just another unknown that's introduced into the process. Just be really aware of the fact that time can really start adding up when it's the evaluation and debug phase. And this is true regardless if you're just an entrepreneur or you're a large tech company. When I was a designer at TI, this is where projects would always fall behind because problems would come up that we weren't expecting, and it would just take us time to find those problems and to come up with solutions for them. This is where most projects tend to fall behind schedule. Just keep that in mind. Also keep in mind that the more complicated the product, the more involved this process is going to be, the more iterations that are going to be required before you can get the product ready for market. And this is true if you have really complex circuits like custom wireless or audio circuits, or a custom fast microprocessor with external RAM memory, you had to route a data and address bus. These are some of the things that I'd mentioned in the PCB layout step that add complexity to a PCB layout. These things just will also affect this process. The more complicated the design, the more likely there's going to be problems. And the more difficult it is for a complex product, finding problems, the problems tend to be more complex as well. The solutions are more complex. So it all just adds more and more time to the process. Just keep that in mind if you have really complicated products, and always try to do whatever you can to simplify your product. That's a huge benefit if you can simplify your product in every way possible. This is a benefit from the minimum viable product standpoint, but from even evaluating your design and iterating and getting all the bugs worked out, it's going to be much better if you can either use like pre-certified existing tested solutions for wireless or a microprocessor. And the final tip is just do not rush through evaluation. The one thing you do not want to do is have problems get through your evaluation and make it to production, because it is a million times easier to fix a problem when you're still in the development phase than it is before you make it to production. I mean, that's a nightmare scenario, is if you have to make design changes after you've started production. You definitely don't want to do that. But you don't even want to rush and do your next prototype, because prototypes are expensive. You want to make sure that you've fully evaluated the prototypes that you have, that you've gotten every bit of information that you can from those prototypes before you iterate to the next prototype. Unless this happens to be something like 3D printing, you have an at-home 3D printer, and in that case, that's something you can iterate really quickly without a big expense. In that case, that's something that's beneficial to iterate quickly. But overall, just don't rush through the process. Make sure you very meticulously evaluate your prototypes before moving on to the next step. And this is to evaluate your Enclosure prototypes and then revise as needed. You get to finally feel your product in your hand, and that's going to be a really exciting moment. Up until this point, you've only seen it most likely as a 3D model, and there's limited information you can get from looking at a 3D model. It's exciting and really enlightening as far as your product once you finally get to hold it in your hand. If appearance is critical for your product, then expect that you're going to need a lot of iterations to get things just right. And it's also just the entire process of developing the enclosure is going to be a lot more complicated if appearance is critical. And that's because appearance is difficult to convey. It's qualitative, not quantitative. It requires a lot of back and forth between you and the 3D model designer. Just keep that in mind, that if appearance is critical, it's just going to add a lot of complexity to the entire process of developing and manufacturing your enclosure. Once you have finalized you'll start with 3D printing, and once you've finalized the early stages of your prototype, basically you've gotten as much information as you can with 3D printing, then what you want to do is you want to transition up the different levels or different types of prototype technology, because each has advantages at different stages of the prototype development process. Start with 3D printing because that's the simplest and typically the cheapest. Then if the plastic material for your product is really critical, snap fits and things like that, then you may want to transition up to CNC machining, which allows you to use the same plastic that will be used in production versus 3D printing resins, which are just made to simulate production plastics but are still quite a bit different. Then once you've got the prototype, right, you've got things like your snap fits and all that working good, but now you're ready you need some samples to show customers. Well, in most cases, 3D printed prototypes they'll look like a prototype. They're not going to look like a production product. I find that CNC machining tends to look better than 3D printing, but still it's not going to have the finish and the appearance of the final product. Urethane casting is a good option for once you're ready you've got the prototype design mostly done, but now you need some high quality samples to show customers. Urethane casting is a good intermediate technology that allows you to produce 20 to 25 parts per mold. Obviously you can make multiple molds, but with urethane castings, they use a silicone mold, and it's soft, rubbery like material. It just has a very limited lifespan. You can get about 20 to 25 parts out of it. Then finally, once you've gotten samples using urethane castings and you've been able to present those to customers, and you've got, hopefully orders or at least interest from customers or investors. But whatever the case may be, once you've gotten enough confirmation of the product that you're ready to step it up and perhaps not go full mass production, but maybe now you need hundreds of parts instead of just 20 parts. And ultimately, you're going to need samples that are going to be exactly like the production units that you'll be making in the future. And the only way to get exactly production units is to use injection molding. That should be the last step, because injection molding is expensive to have the molds made, and it's the most difficult to change. You don't want to spend thousands of dollars on a mold and then realize that you need to make some changes to it. But you can make changes to molds as long as the changes are removing material from the mold, so therefore adding a feature or something else to your product's enclosure, but you can't add material back to the mold, which is the case if you wanted to remove a feature from your part. Then that would require adding material to the mold, and you can't do that. Just make sure you try to get all the bugs worked out before you switch to injection molding. And once you do switch to injection molding, as I always advocate, start simple and then take small steps up from there. For instance, start with a single cavity aluminum mold once you're ready for injection molding. A single cavity just means that mold makes one copy of your part each time it's injected with plastic. That's the simplest you can do is just having a single cavity or one cavity. Aluminum for the mold is important because it drastically lowers the cost of the mold, because aluminum, as you probably know, is a lot softer than steel. But it just makes the mold easier to manufacture, because molds are machined using CNC machining. So machining away or sculpting away aluminum is much easier takes less time than it does to do that with steel. Start with a single cavity aluminum mold. And those can be good for thousands of units, even up to maybe 10,000 or more units you can get from aluminum molds. Start there. Then as your production volumes increase, then you transition to steel. There are different grades of steel, so you can go up harder and harder steels. They'll have a longer lifetime, but they'll also have a higher cost. So just don't take big steps. Don't go from a single cavity aluminum to a 8 cavity high grade steel mold. That's too big of a step. And once you migrate to steel molds, so you have more durability, the mold can produce more parts before it ultimately fails. But you can also increase the number of cavities, and increasing the number of cavities basically acts to lower the cost of each part. It just takes less time if each time they inject plastic in the mold, out comes 2 parts or 4 parts instead of 1. It just increases the cycle time, or speeds up the cycle time, and therefore lowers the part cost. Increasing the number of cavities is a good strategy for lowering your production cost, but don't rush to do that. Don't worry so much in the early days about optimizing every penny of profit. That can come later with economies of scale, and where you can do things like increase the number of cavities, but that all adds to the upfront cost. And in the early stages, you need to always focus on minimizing your upfront cost and not on maximizing unit profit.
If you like this video, be sure to check out this video here, which is a tutorial showing you step-by-step how to design your own custom printed circuit board, or this video here where you will learn about the top 10 product design mistakes you must avoid.